So we have this nice simple criterion that we can travel along S equals I omega, and we can watch out for encirclements by G open loop of -1, 0. So that's fine. And now we have to think about doing that in the real world. So how do we do this? How do we consider encirclements of G open loop? This all sounds quite abstract. And there's a simple way actually to evaluate this. And towards that, we are first going to think again about our time domain. And so if we imagine our chemical process and our input function, so perhaps this is a flow rate. And let's say we are applying a sine wave for our inlet flow rate. So we apply some amplitude and we vary with time. We vary that flow rate along a sine wave. So we fix a certain frequency, and with time, then our input function will vary along that sine wave. And then we observe the response. So as our input is varying with the sine wave, our output will also vary. So the variable, the state that we are observing, that will also eventually follow a sine wave. So it may go through a couple of transitions, but eventually it will settle down to a sine wave as well. And that sine wave will have a certain shift. So it will have the same frequency, but it will be shifted to some extent. So if you can imagine two sine waves sitting one on top of the other, where one of those is shifted to the left or right of the other, then that is accounted for by this theta. The magnitude will also be different. So the magnitude or the amplitude of this sine wave, which we define to be u over bar, that will generally be different to the amplitude that we observe on the exit. And so we can define for ourselves the magnitude ratio, which will be the amplitude of the response to the amplitude of the control. And we've already defined the phase shift by the angle theta. So this is simply establishing some definitions for us. And what we'll do next is figure out how to travel along S equals I omega.